So, last class we saw the disadvantages of distributed system, and previous to that class I think we had discussed about the advantages of distributed systems. So, as you observe the advantage and disadvantage of distributed system, unlike other systems which are available, the distributed systems are usually complex, is not it? So, why they are complex? Because of their topology. I think we started from a small fundamental topologies like star ring, etc. And when you go for hybrid topologies, arbitrary topologies, developing the algorithms for those topologies will be really challenging or complex. That we shall see how to develop distributed algorithms. So, already we have developed a number of algorithms for sorting, searching, etc. For the centralized systems. But if you try to develop the similar kind of algorithms, searching, sorting, the fundamental algorithms, for a distributed system, the algorithms are complex. Why they are complex? Because one major drawback is that because of their topology. Topology changes frequently, that we shall see. And second, fault tolerance. What is fault tolerance? So, whenever you say distributed system, there are several components, hardware components as well as the software components. So, any components can be faulty at any time. So, in the presence of fault, if you design a distributed system which will provide the service without any disruption, then developing algorithms for such scenario will be difficult, will be complex. These situations are usually not faced in the centralized systems. So, one is these are the two important limitations you can say, topology and fault tolerance. Fault tolerance means in the presence of fault in any of the components, software components or hardware components, how to develop the algorithms, how to develop distributed algorithms in the presence of arbitrary topology, general topology or fault tolerance, right. So, because of this the distributed systems are facing lot of challenges. Now, we shall see what are the key challenges and or we call the key characteristics of a distributed system, or I will just list down a number of characteristics. If a majority of the characteristics are satisfied by a system, we can say it is a distributed system. That is also another way of defining the distributed system through the characteristics or properties or challenges, whatever you tell. So, first one is resource sharing. It is also a property of network. In the computer network also resources are shared, but this is also a characteristics and of course, a challenge for the distributed system. Openness, that is extensions or improvement of distributed system. It will be more clear if you consider the microkernel based distributed systems. Their openness will be more, because as in the last class I told you, some of the services which are defined within the kernel or which you call the kernel services, they can be defined at the user level, at the developer level as a set of user services. So, that means that kind of systems are more open as compared to the other distributed systems. Then third, concurrency. So, what is concurrency? We are trying to do multiple activities within a time interval, not at the time instant. Suppose this is activities are there, A1, A2, AM, M activities are suppose there, and if you want to do all the M activities at time instant t, then we can say it is a parallel system, because everything we are doing parallelly, simultaneously at the same time, they are called parallelism or parallel systems. But if I say that A1 to M, all M activities will be performed with a time interval T1 to T2, then we can say it is a concurrent system. I think you understood the difference between concurrency and a parallelism. So, parallelism means true parallelism. So, concurrency gives some kind sometimes true parallelism and sometimes overlap parallelism, like your pipelining system. So, we try to parallelize a number of activities with respect to a time interval, not a time instant. If you are doing something at time instant, then they are simultaneous or full complete parallelism. So this achieving this concurrency in a distributed system is a challenging task, because you want to concurrently execute certain services, and to maintain the concurrency you have to order the events, you have to order the various activities, and the ordering of the activities, ordering of the events is itself a challenging problem in distributed system. Ordering means which task will be done after what, and we should give a guarantee that a task which is arriving late should not be executed fast. So, for that you need to order. Then while ordering, what will happen? For example, activity A1, A2, these tasks are sequenced. You have given an application, and that application has been reduced to a number of activities, and these activities are numbered like this, such that AI should be always this less than, you will understand that AI should be executed before AJ, that we call happen before relationship. AJ should not be executed before AI. That is the meaning of writing AI less than AJ. And if I assume that I is this 1, 2, 3 are the subscript, then I must be less than J numerically, 1 must be less than 2. That means, say, first task will be executed first, second task will be executed second. Then why it is becoming a challenge for a distributed system? Because there is no global clock, but every node is having a clock, right? And because of this local clocks, getting all the clocks synchronized is difficult. If the clocks are not synchronized, the order of activities will also not be synchronized. So, that is why concurrence has become a challenge for a distributed system. So, for that we have a number of time synchronization algorithms that we shall see, or we call the clock synchronization algorithms, and we have some consensus protocols, and at the same time we should have agreement protocols. So, these three are completely different, though look similar: consensus protocols, agreement protocols, and synchronization protocols. So, then fourth challenge is, we shall discuss in detail each of these characteristics will be discussed in detail whenever we discuss about consensus protocol, agreement protocols, and synchronous protocols, or these three set of protocols are coming under these characteristics. Then fourth is scalability. It is above and all, that is your extensibility and expandability. Expandability or extensibility, what it says, that you can go on extending the system in terms of their size, and when you extend the size, the performance will be degraded. But scalability says that you should design a system, you should improve the system, or you should expand or extend the system in such a way that the performance will not be degraded, and if it is degraded, it is within a tolerance limit. That is what the meaning of scalability. So, scalability means expansion of the system to a size where the performance will not be much degraded. Am I clear? I think you should not confuse with expandability and extensibility. So, extensibility and expandability is supported by the computer networks, but distributed system supports scalability. But achieving this scalability is a challenge. Suppose you have 10 computers and 9 computers failed, still one computer is there. So, you will get the service, but not same as having a 10 node system. So, there the performance will be degraded, and perhaps we may not achieve the actual goal of performance. And the major goal of scalability to improve response time. So, what is response time? When you put a query to the system and when the first results appears in the form of output, that duration, suppose at time t you put a query to the distributed system for getting some answer, and that answer may depend upon a huge number of hardware and software in the background, and finally it will produce the result which will give to you. And when you get this result, for example, it is time t2, and when you put the query at time t1, and complete result you are getting at time t3. I am talking about the first result. So, the duration from t1 to t2 is known as the response time, and that depends upon latency of the system. I think it is clear. So, response time is the time duration when the user puts a query into the system and till the first result comes on the screen or first result appears on the output. But it is not the complete results. Complete result may take several few minutes or few hours also. We are not waiting for the complete result. When the first result appears, that is the response time, and we have to improve the response time. And when you if you do not focus on this scalability, what will happen? The response time will be more, and the response time is directly proportional to latency of the system, and the latency depends upon the various hardware and software. Suppose if I replace a new hardware whose performance is better, whose clock frequency is better, or it has a multi-core processor. I will just replace a node from the distributed system which has multi-core processors. Then certainly the latency will be improved. That is the hardware latency. Similarly, how to achieve the protocol latency or software latency? By developing various communication protocols. MAC layer protocols, as I told you, data link layer protocols, network layer protocols. So, by developing those protocols also we can contribute to the latency, and if the latency is improved, your response time is also improved. So, therefore, this scalability, latency and response time, they are somehow related, and how they are related, that we have to focus. Or in other words, I can say scalability is a function of latency or response time. And what is that function? What does it depends? That we have to find. Then fifth one is fault tolerance. What is fault tolerance? So, when a distributed system is designed, if any component, hardware or software component fails, the system should not stop. System should continue to provide the service. There should not be a catastrophic failure. For example, a 10 node distributed system is developed. Until 9 nodes are faulty, the system will provide the service. At least one node should be working. But if all the 10 nodes are not working, then we can say it is a failure. So, in the fault tolerance, we can assume that a minimum number of components are working and the rest of the components are likely to be faulty, or there is a probability that some of the components of the distributed system will be faulty. So, if it is faulty, the task which were assigned to those components will be taken out and will be assigned to some of the nodes which are fault free. So, for that what we have to do? For that we have to find out which nodes are faulty and which nodes are fault free, so that faulty nodes can be isolated either before assigning the task or dynamically the moment the fault is found, the task can be taken out from the node and can be assigned to some other node. So, there are two ways, one is static way, another is dynamic way. Static way means whatever the condition is available, that will be fixed till your fault tolerance algorithm completes its execution. Dynamic means at any time the fault can happen. While your algorithm is running, it has to take care of the change of the state of the node. The node can make a transition from fault free to faulty to fault free to faulty, like that. They keeps on changing also. But how to keep track that? How to know that which node is faulty and which node is fault free? And if it is faulty, how long it becomes faulty? Or if it is permanently faulty, then it will be completely faulty till the execution of the algorithm. So, all these issues will come the fault tolerance, and this fault tolerance is a very what do you call, extremely important topic, particularly for the safety critical distributed systems. Safety critical distributed systems means here the faults cannot be ignored, and if the fault occurs, at any cost you have to solve the problem, whatever may be the cost. The only trade off will come for the cost. It is not that we can't achieve the fault tolerance for every system, but if the system is safety critical, for example, a huge cost is involved or a person's lives are concerned involved, then you have to achieve the fault tolerance at any cost. Because till today's there are different techniques to achieve the fault tolerance. I am just telling the basic technique, the replication or we call redundancy. For example, a flight system, instead of having one engine, let us go for two engines. If one engine fails, the other engine will take over. And if you want to make a system completely robust, what you have to do? Go for three engines. If the only when the three engines fails, then there is a failure, but that is very less. Therefore, most of the rockets which are launched, so they have at least three engines, at least three engines. When the satellites are launched with the rockets, so rocket has at least three engines. Assuming that any engine, at least one or two engines may fail during the traversal, because it takes 3 months to 4 months to reach to the moon or what to the anywhere space. So, and if you go for more than 3 engines, the cost is not affordable. The experiment has shown that if you go beyond 3 engines, if you have 4 engines, no country can afford the cost. 3 engines the maximum possible, and if all 3 engine fails, then there is a failure. Am I clear? And if you have only one engine, then you might be thinking how it is difficult, right. So, therefore, how to achieve fault tolerance, that itself a topic of the distributed systems, and we can achieve various kinds of fault tolerance algorithms with respect to different fault scenarios that we will be discussing in this. The next is 6, transparency. I think this also we have discussed. What is transparency? It hides the complexity of the distributed system from users or application programmers. I already have told you distributed system is a complex because it has large number of heterogeneous components, topology is different, and if you want to achieve fault tolerance, there is every possibility that different kinds of faults can occur in the system. So, due to these complexities, the design of distributed system is complex, but this design may be complex for the designer who is designing the distributed system, but it should be as simple as possible for the users and application programmers. So, there the task is not finished. So, after designing the system, the design is so complex, it should not be known to the also users. You have to conceal the users from the complexity of distributed system, that is called transparency. You have to hide all the details of the complexity. User will never feel on the background the system is so complex, right. So, particularly when you go in a flight, the flight internal system is so complex, but the passengers they are not able to know. They know that we are starting from this source and we have to reach at the destination, but the system is so complex they are not knowing. So, that is again achieving this transparency is really a challenging task. So, if you see, the transparency is one of the very important property, characteristics, challenge for a designer. For user it is very simple, because user will feel I am working on a PC, I am working on a single computer, but in the background a huge computers, a huge number of nodes, softwares, operating systems are there, you will not be able to know. That we call it is single system image, SSI property. This SSI property, single system image property, has to be achieved in a distributed system, and it is a challenge for the designers. So, this transparencies, since it is a challenging topic, again they have divided the transparencies into 6 types. First one is okay. So, these are the various types of transparencies you need to achieve. So, the access transparency is very clear. That means, when the user accesses the distributed system, he is accessing that a single hard disk, single memory, single processor. that is a very logical in nature, but physically there are several processors, several memory modules and several hard disk. I think it is very clear. So, you have to achieve the access transparency, you have to give an illusion to the user that he is using only one system, having one processor, one memory and one set of IO devices and one type of operating systems also. So, how to achieve this, that we shall discuss. How to design an operating system such that we can achieve the access transparency. So, when you go to the design of distributed operating system, you will see that all these features will come. We will have the proper services. It may be implemented later in the kernel part or in the user service as a user service, but these will be made available in the form of services. So, whether it is user service or kernel service, remember a distributed system consists of set of processes P1 to Pm, m processes, and each of the process is considered as a service. And once when one service is taken as a client, another service can be a server. A service itself can be a client also, and a chain of services will work to and they will cooperate in such way that they can solve a single problem irrespective of the location, irrespective of the kind of operating system and irrespective of the language support. All will be cooperating for solving a single task irrespective of the location. Suppose one process is at India, another process may be in USA, and both they combine and work together for solving a single problem, right. So, these things we shall discuss, but I can define that set of processes can constitute a distributed system, or a distributed system is nothing but set of services, where every service is a process, and every process again fundamentally a running program, a small module, and that module can be doing a hardware function or it can be doing a software function. Basically, it will be managing a resource, it can be software resource or it can be hardware resources. And how to execute these services in a best possible way, that is our goal, right. So, next is location transparency. What is location transparency? That if the machine 1 is there here and machine 2 is here, so machine 1 will be calling a service and implementation of that service, execution of that service will be done at a remote machine and the result will come back here. Now, the user is sitting at machine 1. So, user will feel that I have put a query into this machine and I got my result in my machine, and my machine executed everything, my executive implemented everything, and all data, program, everything are available in my machine. But in reality what happens, physically what happens, for doing this user's query or user task, some of the tasks have been done at a remote place, and that location will be concealed from the user, and that is called location transparency. The location of the services remain ignored to the machine 1 user. That is just an example. So, for every user, he will never feel about the location of the services, he is only worried about the services, and if you can hide the location of the services from the user, we call it as location transparency. Am I clear? Then migration transparency. For example, your one user has put a query or for running an application, and that application process consists of several processes P1, P2, P3, K, suppose K processes. K processes are to run or to be executed for accomplishing that task. So, these K processes may not be available at the machine 1. Some of the services or processes are available in some other machines, right. So, when we try to execute some of the processes at the remote machine, so these processes are to be migrated from one place to another, and when they migrate either for with some goal for achieving the speed, because if I execute process P2 in machine 1, it may be taking 2 microseconds suppose, but if I get a better machine somewhere in the world, I will send this P2, this P2 will migrate to that machine where the execution can be done within 0.5 microsecond, 1/4 of the time we can save. And this migration should be so frequent that will be known, that will not be known to the, then there are two type of migration. So, when process P2 is migrating to another place in another machine, it can keep a copy in the local machine and a copy will be transferred only, and that copy will be executed on the other machine, and this P2 at this machine will be waiting for the result from that machine. That is one way, or completely P2 can be transported. There will be no copy kept here, because if you are keeping a copy, since the same P2 is replicated, so the size of the process will increase and there will be requirement of storage, and we shall discuss about the various types of migration and how to implement those migrations in the distributed operating systems, because this migration was not a issue for the centralized operating system as far as the resource management is concerned or the process management is concerned, but in distributed system migration has become problem and it is a requirement, right. So, how to achieve this migration transparency? When the process migrates from one machine to another machine, and what are the advantages of also migration, what is the disadvantage of the migration, and which commercialized operating systems, distributed operating systems supports migration. All these issues will come in when we go to the design of the distributed systems. Then the replication transparency. Why the replication is necessary? Already I have told you, for fault tolerance, redundancy. So, instead of having one process, let us duplicate that process once more, and let us allow this process to run in two different machines. If one machine is faulty, at least the other machine is fault free and it will be giving the correct result. Am I clear? So, that is called replication transparency, and again you can have 3 replicas, you can go up to 4 replicas, but maximum you can go up to 7 replicas, otherwise your system overhead will be very high, which cannot be affordable. Or in other words, I can say you can go for 2k plus 1 replicas. That is a very well known model, 2k plus 1 for tolerating k failures. If you want to tolerate k failures, you can go for 2k plus 1 set of processes, or for if the k is equal to 1, at least you have to use 3 processes. Assuming that 2 processes, whatever the results they give on the majority basis, we have to accept it, and the process which is giving a single process which is giving incorrect result, that can be masked, that can be ignored. It is okay. So, maximum k value can be 3, not more than that. So, 3 into 2 6 plus 1 7, as I told you, 7 is the maximum affordable cost of replication. And when I say the replication, it can be software or it can be hardware, that is what I am telling. So, service replication, everything is service. Even if you want to manage a hardware, for that you have to create a process, and that process is becoming a service. Am I clear? So, if you want to manage a software or you want to manage a database, for that you need a process, and that process is becoming service, and that service has to be defined and it has to be published. Published means it must be open to the user, so that user as and when requires it will use. It should not be a part of the operating system, and we shall identify which services are the kernel services and which services are the user services, and how the user services interacts with the kernel services. What is the restrictions, right? So, for allowing the user services to access the kernel services, we need set of system services, or we need set of system calls, and those system calls must be defined in the kernel of the operating system. So, there the challenges comes how to achieve inter-process communication. If the user service is a process, kernel service is a process, and user wants to communicate with the kernel. So, there are communication between 2 processes, right. So, all these issues will come again on the design of distributed system. Then next is concurrency transparency. What is concurrency? Already I have defined what is concurrency. So, several processes will be executing with respect to a time interval, and at different machines at different places, several services, and that will be remain transparent to the user. So, but what user will feel? It is user will feel it not concurrent. He will feel it is completely parallel, simultaneous, true parallelism. I gave my data, I gave my query, I got the result, and the system has done everything parallelly. Parallel means at the same time. Just because the human eyes can only perceive in terms of second, it cannot perceive in terms of microsecond, nanosecond, but the system services may take several microsecond. For a human being, it gives in second, and human will think as if I gave just this task and I got it. That means as long as user is getting the services in terms of second, response time in terms of second, user will feel these transparencies are there, right. So, next is scalability. What is scalability? There can be several faults, there can be several systems giving a less performance, but user will feel the system is good, system is response time is good, and the systems is having a scope for scalability, that should be transparent. How? For example, I want to search 100 items, my system gives in terms of second, user could not fill. Now user will give 1000 elements to sort, it will take same time for as 100 for the user, but in reality it is not same. I gave 100 items to sort, I got the response time, immediately 100 items are sorted, and I gave 1000 items, 1000 items are sorted, but time will be different internally, which can be noticed by the designer, but user will not feel because everything coming in second. That is what the scalability. That means as you go on increasing the complexity and size of the problem, the performance will not be degraded much, so that user will feel happy, okay, whatever I am giving, I am getting it. And when the performance will be coming to notice, for 100 if you give data and if you give 1 lakh data item to sort, there will be a slight difference, that will be allowed. But for 100,000, for a moderate size of data, it should give the same performance and everything will be hidden to the user. Am I clear? So, that is what the scalability transparency. Then performance transparency, that already I have told you. Performance should be maybe degraded in the background, but in the foreground performance should be satisfactory, and that satisfactory level depends upon the applications and the user's expectation. Suppose user wants that as long as I am getting the performance in terms of second, it is good, but if it goes in terms of hours or minutes, it will not be tolerated. For example, you are in a queue in the bank. If it is taking 10 minutes to 15 minutes, it is okay. Till 20 minutes, 30 minutes, you will have patience. But if the bank people will tell you wait for 2 hours, will you tolerate? There the performance is degraded. So, that is the meaning of performance. So, performance should be obtained in such a way that user will feel it is okay, the performance is good. Then failure transparency. User will not be worried about that some software and hardware components may be faulty on the background. He wants the service. So, if there are 10 node system and 5 nodes are not working, 5 nodes are working, your system should give the result to the user, and user will know, will not come to know that the 5 nodes are faulty in the background. I gave a query, it got the result. So, what you have to do? As a designer, all the 5 faulty node tasks should be migrated to the fault-free nodes as and when the fault is encountered. As soon as you encounter a fault, let us migrate this task to the other fault-free nodes. There it will be executed and user will get the service. Am I clear? So, this achieving this failure transparency is itself a challenging problem, and we shall see when the failure complexity is more. There are some failures which you cannot predict. We cannot. There are some failures you can predict. For example, I put a battery in my mobile phone. I charge my battery. I know that it will just last for 12 hours or 24 hours. Then I am recharging it. I know that maximum it can go for 24 hours or 32 hours. Depending upon the today's technology, a battery how long it can stay for a mobile phone? 12 hours, 24 hours. Yes. Similarly, here I know that these are the predictable failures. What kind of predicted failures? If I am using a machine today I cannot say that today it will be faulty, but if I am using a machine which is 10 years old, there is every probability that that machine may be down at any time, all right. And there are some failures we cannot predict, like lightning. Even in the rainy season, you cannot expect that when the lightning will occur, when the natural disaster will occur, and those problems are called Byzantine failures or arbitrary failures. So, how to develop algorithms to tolerate the Byzantine failures, Byzantine or Byzantine failures, right? And sometimes the people call arbitrary failures or general failures. So, developing algorithms for Byzantine failures is a really a challenging task, or a very in the distributed system domain they call it is Byzantine's generals problem, BGP, Byzantine generals problem. And for small failures, simple failures, it is good. For example, if I know that my machine will be crash or hard faulty if it is not powered or it is physically damaged. If a mobile node is physically damaged, fall down from your hand, that is a crash fault. That we can easily give a solution. In the place of one mobile phone, you will go for a new mobile phone, is not it? But if a failure is a short failure, mobile is working, but signals are coming, but you are not able to talk. Signals are not transmitted. That may be happening sometimes. You may be receiving the calls, but when you talk, your voice is not reaching to the destination. That means mobile is not hard faulty, it is working, but partially working, right? And I will give another example. You are talking in a mobile phone, but your voice reaches after 5 hours. Is there any use? And you receive a call that at the source he is somebody, your friend is calling, but you are listening after 2 hours, 3 hours, 1 hour. There is no use. But system is still fault free because the communication is going on. Okay. So, that is called delay failures. They are all coming under short failures. So, how to handle hard failures, and what are the different types of hard failures, and what are the different types of short failures, and what are the different Byzantine failures. After knowing the characteristics of different types of failures and the causes of failures, what are the different causes for which the system components are faulty. If the battery, for example, if the mobile node is completely damaged, physically damaged, that is a crash fault. But another crash fault example I am giving, your mobile phone is working, but battery is not there, charge is not there. It is as good as physically damaged. Unless you charge it, it cannot work. But there is a difference between two failures. How to handle those situations? So, I am just giving a mobile example. Let us go for a data center. In data center, it should be working 24 hours online. If it is not working for 1 minute, the entire world will be stopped, right. So, therefore, each of these components, how they are faulty and what are the probability of failures and which components are faulty at what time, all these issues will come under the fault tolerance. But this may be a challenge for the designer, but user is not concerned. What type of failure? I want the service, that is all. User wants the service, but the system can be faulty. There may be several problems may be there while designing. All these issues will not be coming to the user's domain. That is the goal. That is the goal of designing a distributed system. So, we shall see some of these transparencies and some of the issues which we have already discussed. They are also goals of the distributed system. It is very difficult to identify which is the goal of the distributed system, which is the characteristics, what is the challenge, what is the properties, and what are the requirement of distributed system. There is a little bit confusion, but goal is very clear. One is that we have to improve the latency at any cost. So, the moment you improve the latency, you got the response time. From the response time, you got the performance, you got the concurrency. Most of the properties will be satisfied. When you try to satisfy your goal, you can see that most of the properties are satisfied. And if the majority of the properties are satisfied, whatever we discussed, then we call that system is a distributed system. That is why sometimes people claim a personal computer is a distributed system. Why? Because it is also running set of processes and there are inter-process communication, and nowadays many single computers has multi-core processors, and it is possible to design many processors in a single machine. It is possible to have different types of RAM modules, and you can have multiple hard disks. So, a single computer is also a distributed system, but some of the properties they may be missing. But what is a true distributed system? Which will be satisfying a majority of the important properties. I told how many properties? I have just listed down some 8 or 9 properties. If majority, for example, at least 5 properties are satisfied for a system, then we call it a distributed system. Otherwise, anything can be a distributed system. Your mobile phone can be also a distributed system. Now, people are going for, in the 5G technology, you will get multi-core processors in mobile phones, and it may so happen that you can run multiple operating system in the same mobile phone. Multiple operating system is also possible. Multiple hardware units are there, and due to the development of IoT technology, you will find a lot of IoT devices will be integrated into the mobile phones, right. So, then that is also a distributed system. And in the next class, I will give an example of a typical peculiar distributed system, which you may not feel, or you may not say it is a distributed system, but still it is also a distributed system. I will give a distributed system which is very generalized one. Everybody will agree really it is satisfying all the properties whatever we discussed, that is a distributed system. And I will give another example of distributed systems which is very restricted, but still it is called a distributed system. So, that means we are going for a very unrestricted distributed system to a restricted distributed system. Okay. So, that we shall see how to balance the challenges of the distributed systems in various application domains.